Okay, so welcome to our Network Plus N10006, Chapter 5. This is about addressing. This is always a good topic because this is always one of the hardest topics for people to understand. And this really isn't super hard. It's all about practice and being able to have a good understanding from the very beginning. A lot of people try to explain it multiple different ways, and it's confusing for a lot of people. So I think I do a fairly good job. I've done other videos dealing with our addressing, but yeah. So some of our foundation topics are going to be our binary and hexadecimal numbering, our IPv4 and IPv6 addressing, assigning our addresses, and subnetting. Subnetting is always really good because we spend a good amount of time subnetting. So working with an IP address, first of all, we have to understand some things. How are decimal numbers represented in binary format? We have to understand how our IPv4 addresses are made up, the different types of addresses, unicast, multicast, broadcast. What are some of the available options? And what are some characteristics for new addressing like IPv6? So when two devices on a network communicate, they have to have some type of local address. Normally, if we're dealing with local addresses, that could be a LAN. But if we want to leave our LAN, we have to have some type of logical address, an address that can change, that can be manipulated. So modern day networks use the IP addressing scheme. There are two types, IPv4, which is 32-bit, and IPv6, which is 128-bit. Binary numbering conversions. So binary is a base 2. In our everyday life, we're used to a base 10. So there's some differences. Also, one of the nice things about binary, like hexadecimal, is we can represent every number in binary. That is not true for all other numbering systems. Like base 8 or octal, we can't represent all numbers. Base 2 we can. Normally we do this built off of a uh, numbering system when we start with 1 on the right and we just keep doubling. So the very beginning, 2 to the power of 0 equals 1. The second spot is 2 to the power of 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8, and it just keeps doubling. So this is a positional method, and when we have an address like 100101110, we take where the ones are at and we add them. So we add 128, we add 16, we add 4, we add 2. So 128, 16, 4, 2 equals our decimal number 150. And you have to have time with this. Now when we're going from a decimal to a binary, normally it's subtraction. We take, for example, 168. Is 168? Does 128 go into it? Sure. 128 does. So we have to put a 1 there. The remainder, we try to take out of 64, which happens to be 39. So does 64 go into 39? No. Does 39 or does 32 go into 39? Yes. With a remainder of 7. And so forth and so forth and so forth until we get the number 101001111. Just to double check, we add up where the ones are, and that should equal back our 167. We need to be able to go both ways, decimal to binary and binary to decimal. Our addresses are, like I said before, 32-bit, and they are groups of 8. So there are 4 groups of 8. So each group of 8 is an octet. So here we have a binary, this is the decimal number, But if you take that number and convert it to binary, it should be 0, 0, 0, 0, 1, 0, 1, 0. And that's going to be our first 8 bits, dot 0, 0, 0, 0, 0, 0, 0, 1. That's our second 8 bits, 0, 0, 0, 0, 0, 1, 0. That's our 2. 1, 2, 3, 4, 5. And there is our number 3. So that's how we get all 32 bits. Each one of these is 8 bits. Now they could be zeros, but they're still part of our 8 bits. Here's a better example. So our structure. Normally, we can group our addresses, and those groups are called subdivided or subnets. And we have to have some type of mask that will allow us to group our addresses. And here is our subnet mask. And this is the really confusing way of explaining it, but that's how our book explains it. I've already done videos on subnetting, so if you want more in-depth subnetting videos, visit my subnet videos. So here we have a class A network or a 255.0.0.0 subnet. Essentially, this part is our IP, this part is our subnet. Our 255 say what numbers are locked in. These numbers cannot change. All numbers that way can change. Numbers that way can't. This, they can. Back before the internet became super popular, we did what was called Classful addressing. So we have 5 types of classes, even though realistically people need to know the first 3, Class A, Class B, Class C. So Class A is if the first octet is between 1 and 126, Class B is between 128 and 191, Class C is between 192 and 223. The rest of them are special classes, and that's not important right now. In each class, there's a predefined classful subnet. 255.0.0.0 is our Class A. Class B, we lock in the first 2. Class C, we lock in the first 3 octets. Again, we can manipulate wherever there's not a 255. Manipulate means we can play with or change. Lastly, is in each of our classes, we included what was called private addresses. Private addresses are what we can use at home or on private networks that do not go on the internet, without some type of mechanism that will mask our private to a public IP address. Our private IP addresses are, for our Class A, anything in the 10 network. For our Class B, anything that starts with 172.16 through 172.31. Our Class C is any network that starts with 192.168 through 192.168.255.255. Those are private addresses. Those are what can be used on private networks like home. So a few addresses that weren't really there were loopback addresses, and that was anything in the 127 network range. That's a specialized address. And there is an APIPA address, and that is a 169.254. If you're not given an address, you will get a APIPA address. That allows just local communication, but nothing other than local. So let's talk about our Class A. If we're looking at the IP address 114.56.20.33, what is the network portion and what is the portion that can change? That's called our host portion. 255 means we lock in the first number. Those can change. Those cannot. With a class B, the first two are locked in. Those can change, or those cannot change. The last two can. With a class C, we lock in the first three. The last one is able to be changed. Types of addresses: unicast, multicast, and broadcast. A unicast is one-to-one, a multicast is one-to-many, and a broadcast is one-to-all. Here's an example. A unicast, this guy will go to one device, not all. So we have to send two packets if we want to receive or go to two different computers. If we send a broadcast, it's going to be one to everyone. If we send a multicast, it'll be one to a select group. So our anatomy of an address. We have an IP address, which again is 32 bits. We have a subnet mask, and that's going to tell us what's our network versus what's our host bits of our IP address, or what can and what cannot change. When we're dealing with addresses for a computer, we have to include a few other pieces of information, like what is our router or default gateway address? What is our DNS or Win server information? There are additional network resources that our computer needs to get internet access. We can assign our addresses one of two ways. Statically, meaning manually. It's simple, you go in, you manually do them, but it's time consuming and it's prone to error. And it's not really good for large networks. It's really good for static resources that may not move often. For example, printers. Or we have a dynamic option, which is normally sent via a DHCP or Dynamic Host Control Protocol server. And that means dynamically or automatically assigning addresses. The old protocol was bootp, and our new one is DHCP, which is based off our bootp. They assign all the information that's needed. Again, another one is our APIP. That's a 169.254 anything. Subnetting, that's our groupings. So how many addresses can we have if we subnet? Because again, subnetting, we lose addresses, but we modify it so that we can organize things better. So we can make more efficient use of addresses. If we're dealing with a class A, each network can have about 16 plus million addresses. Class B can have 65,000, Class C 254 addresses. Again, that means if we have one Class A network, we have 16 million addresses. What happens if we only need 10? Well, we have 16 million. Even if we only need 10, we have 16 million. So we have this concept called Classful addressing, meaning we don't care what the class is, we'll just manipulate the subnet mask depending on our needs. We'll get into that a little bit later. Our subnet notation could be in dotted decimal, in binary, or in prefix or CIDR or slash notation. This is just how many ones out of 32 bits will be ones. Here we have 8 bits of ones, /8. You'll notice they're always continuous ones. There'll never be a 0 and a 1. They'll just always be all ones until there are zeros. So calculating our subnet. So if we're creating how many numbers of subnets we need, we can do 2 to the power of how many borrowed bits. If we're looking at how many numbers we can assign, we'll do 2 to the power of x minus 2. So if we're going to borrow 2 host bits, we can have 2 to the power of 2, which will be 4, and we minus 2. That means 2 addresses per network. That gets a little bit confusing, so let's go over that one more time. So if we're borrowing 2 bits, we'll move to a /26. So we're borrowed 4 bits. 2 to the power of 2 is 4, so we'll have 4 networks. If we are dealing with how many addresses we need, we look at the /26. There are 2 network bits. The remainder are zeros. So that means there's going to be 6 zeros in that remaining octet. 2 to the power of 6 is 64. We minus 2. If we have a /26, we can use 62 addresses per group. I do not like the way our book explains subnetting, so again, if this is confusing, go back to my videos on subnetting. They will be more helpful. Classful versus subnetted. Classful is, if it's a class A, it's guaranteed a 255.0.0.0 subnet. Usable IP address ranges, they cannot overlap. They have to be unique, like home addresses. We will always have a network ID. We will always have a end or a broadcast address and a range that's in the middle. So network, that identifies, and a broadcast, which is our end. We have what's called a CIDR, and that is using summarization for route aggregation. Basically, we look for where things are similar. Here, these numbers are all similar. These ones are not. So we could summarize it by doing 192.168.30.0. That's 192.168. Add where the ones are at. That happens to be the 32 spot. And we count out how many octets we're using. /22. That means the 22 bits cannot be changed. The remaining 10 can be changed. All right, lastly is our IPv6 addresses. We're going to spend some good time on this. So don't think that this is just going to be the first time we're exposed and that's it. I have a lot of IPv6 videos coming because this is hard material. We're running out of addresses for IPv4, hence the use of the IPv6 addresses. 2 to the power of 32, about 4 billion addresses. 2 to the power of 128 is 340 undecillion addresses. So there are some benefits, more addresses. There are some problems. No broadcasts, no fragmentation. We can coexist with IPv4, and headers are simplified. So here's an example of our IPv4 header. Crazy. A lot more information. With our IPv6 header, way simplified. IPv6 address could be, well, it is in hexadecimal. So we're moving away from our 4 groups of 8 bits, and now we're going to each hextet, 1, 2, 3, 4, 5, 6, 7, 8, 8 hextets with 4 hexadecimal numbers per hextet. And when we have lots of zeros, we can actually remove leading zeros, and we can do a double colon, which we're going to get into that because there's some rules for a double colon. We can only use our double colon once, and we can only use it for a string of zeros. In IPv6, we still have unicast and multicast, But now we have Anycast. Unicast is the same. Multicast is the same. Now we have Anycast, and traffic travels from a single source device to the nearest multiple but specific devices on a network. So similar to a broadcast, but not the same. That's actually it for this chapter. Again, go back for subnetting. We need to understand subnetting back and forth so that we can really dive deep in our networking concepts.